This video is a demonstration of stack data management on applications for limited local memory multi-core architectures. One such kind of architecture is the IBM cell processor. We will test it on an example which is called rcount. As we can see, the return value of its base case is 0. In other cases, the function will call itself. As a result, the execution result will be n for any input of n. Two versions of the applications will be shown in the video. They are running with the same application, except that rcount no is the version running without any stack data management, and rcount yes is the version running with our stack data management technique. Let's first look at the versions without stack data management. Before we run, let's first compile it. Now we can try to input a small n, let's say 100. As we can see, the program is successfully executed. Now let's try a larger one, let's see 7872. The program works well too. How about 7873? Uh-oh, the program fails. The same thing happens for n equaling to 80,000, which means the application runs out of the local memory. To be more concrete, we can take a look at our explanation. As we can see, each time when the rcount function calls itself, the stack size will increase. Eventually, the stack data will go to the heap region or global region and corrupt the program. This slide shows what we will do for stack data. On the left-hand side, we can see the function f1 calls f2. f2 will call f3, which calls f4. The table contains the stack frame sizes for those 4 functions. Now, let's see what will happen when the program goes. Each time when a function is called, the stack increases. But when f4 is called by f3, there is no space in the local memory. To be able to enable the execution of the program, we need to evict the old function frames as many as possible to make room for the coming function f4. Here we only need to put function frames for f1 and f2 to the global memory. Our stack data management only keeps the active portion of application stack in the local memory. We choose the granularity of stack frames when the eviction and fetching of frames is needed. The granularity means the minimum transfer unit between the global memory and the local memory. Our scheme is a pure software technique. It contains 2 functions, FCI and FCO. FCI checks the available space in the local memory before a function is called. When the remaining space is not sufficient for the coming function frame, it will automatically move old frames to the global memory. On the contrary, FCI guarantees the caller frames exist in the local memory before the callee returns. If the caller frame misses, FCO will get it from the global memory. FCI will be inserted just before each function call, and FCO will be inserted right after each function call. The graph shows the flow of using our infrastructure to manage stack data. Giving our C source code for SPE, our optimized compiler will automatically insert function calls at the right place and generate the executable files. This completely eliminates the laborious insertion work for programmers. Now, let's see what will happen when the application runs with our stack data management. Before we run, let's compile it. As we can see, the only difference from the previous make script is the flag LLM manage. This flag will trigger our implemented path in the GCC to insert library function calls. Now, let's try to run it with an input n equaling to 7872. As we can see, the program works well. A larger input value of 7873 still works. An even larger value of 90,000 still okay for the program. That's to see, our technique enables unlimited stack use in the local memory of limited local memory multi-core architectures.